All right, lecture 3 of VCE Specialist Maths Units 3 and 4. We're going to look at sequences and series, and these are the topics that we're going to cover. So we're going to look at what a sequence is. We're going to look at arithmetic sequences, arithmetic series, geometric sequences, geometric series, infinite geometric series, and combined recurrence relations. It's going to get pretty hairy towards the end, but hopefully we can make some sense of it. I'll put timestamps on the video so you can jump to the relevant part for you. Let's begin with what is a sequence. So a sequence is a list of numbers where the order is important. So you'd be familiar with sequences from primary school where they ask you to sort of fill in the next number. If we look at this sequence here, it goes 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. Pause the video, have a think about what the sequence is and what comes next. But hopefully you're recognizing that this is what's known as the Fibonacci sequence. And basically you get every new term by adding the two previous terms together. So 1 plus 1 gives us 2, 2 plus 1 gives us 3, 3 plus 2 gives us 5, and so on. So we can see that, yeah, it's a sequence. It's a list of numbers where, yeah, the order is important. So if we look at this, if we consider 0 to be the 0th term, then this sequence is, then the number 8 here is the 6th term, 0, 1, 2, 3, 4, 5, 6. So it's the 6th term, and the notation we might use around that, say t sub 6 equals 8. So the 6th term is 8. Okay, more generally speaking, we'd say for a sequence that t sub n is known as the nth term. So yeah, t sub n is the nth term. T sub n minus 1 is the term before the nth term. So if we look at setting up a recurrence relation is going to allow us to generate a sequence. That's essentially what it does. Basically, we're going to look at what the first term is. So t sub 1 equals 4 in this case. Okay, what this next part says is, it says t sub n equals t sub n minus 1 plus 3. So what's that saying is to get your next term, t sub n, take the previous term, t sub n minus 1, and add 3. So I encourage you to think about what this sequence would be. But I think you would agree the first term is obviously 4, because that's given to us, and it has to be given to us. Second term is going to be 7. Third term is 10. We're just adding 3 each time, right? So this recurrence relation defines this sequence 4, 7, 10, 13, 16, 19, and so on, right? So what we can say here is, from now on, what we're going to say is we're going to consider T1 being the first term. But in this instance here, the Fibonacci sequence, I actually just think it's an interesting example, and it allows us to generalize a little bit and think a bit more abstractly. We've actually got two first terms. The Fibonacci sequence is defined as having a 0th term and a first term. So I encourage you to pause the video and see if you can work out what the recurrence relation would be for the Fibonacci sequence. And just keep in mind that it's actually going to have two first terms. 0 and 1 are defined as t sub 0 being 0 and t sub 1 being 1. So in the Fibonacci sequence, again, it tells us the first two terms. And I think you would agree to get every other term, you take t sub n minus 1 and add t sub n minus 2. You add the previous two terms. So for example, to get 8, we add 3 and 5. So 5 would be t sub n minus 1, and 3 would be t sub n minus 2. Okay, so I'll just write it another way here to help. Yeah, so in the case of the 6th term, t sub 6 was 8, so t sub 6 is t sub 5 plus t sub 4. So that's just 5 plus 3. Yeah, 5 plus 3. Okay, here's a picture, AI generated, Leonardo Fibonacci, 1170, excuse me, to 1240. So he lived a long time ago. All right, let's have a look at arithmetic sequences. So an arithmetic sequence is a sequence where the next term is found by adding a fixed amount to the previous term. So an arithmetic sequence might look something like this: 2, 5, 8, 11, 14, and so on. Pause the video, see if you can work out what that is, but you're just adding 3 each time, I think you would agree. So what we would say is this: we can actually define what's called the nth rule for the arithmetic sequence. If we define the nth rule, we'd say, all right, we take this first term, we're going to call this first term A. So A is the first term. Yeah, so let's go back a bit for a moment here. So I just wanted to define the recurrence relation because we just jumped from the recurrence relation to the rule. I just wanted to explain this with the recurrence relation. So this sequence here, 2, 5, 8, 11, 14, would have this recurrence relation. So T sub 1, which is the first term, is T sub n. T sub 1 is the first term, which is 2, and then T sub n is equal to T sub n minus 1 plus 3. So basically, to get your next term, take your previous term and add 3, right? Okay, then what's in this box here is what's called the nth rule. Or how do we do this without having to use the recurrence relation? Because you think you might agree this could be cumbersome, especially if you've got very large n. So what we say is this is the rule. So to find the nth term, you take A, which is known as the first term, or T1, and then you add n minus 1 groups of D, where D is the common difference. Okay, so if we look in this case, the common difference is 3. So if I needed to say get to the third term, which is 8, I would start at 2, and I would add 2 groups of 3. So that would add 6. So I'd get from 2 to 8 by adding n minus 1. Okay, remember 3. The nth term, the example I was using was 3. So n minus 1 would be 2. So add 2 groups of the common difference to the starting point, which was A. Okay, the common difference is simply very easily found. You take tk, so whatever some number is, and then you subtract the previous number. So tk minus tk sub k, t sub k minus 1. So 5 minus 2, or 8 minus 5, or 11 minus 8. And that will tell you what the common difference is, which is D. So that's what we call the nth rule for an arithmetic sequence. Let's look at an example. Hopefully it will clarify things. Find the 10th term of this sequence. So, yep, same sequence, 2, 5, 8, 11, 14. Okay, we're going to use this rule. So we want to know the 10th term. So we're going to do T sub 10. Okay, we know the first term is 2. So A is the first term, which is 2. Okay, we want to get to the 10th term. So we're going to do n minus 1. So 10 minus 1 is 9. 9 groups of 3. So it's 2 plus 9 times 3, which is 2 plus 27, which is 29. And sure enough, if I generate that sequence down here, this would be all the sequence. This is the sequence that we're talking about, up to n being 30. So this is the 30th term. And sure enough, the 10th term is 29. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that is an arithmetic sequence, recurrence relation, and the nth rule. Okay, let's look at an arithmetic series. So a series is this idea that we're going to sum all the terms in an arithmetic sequence. So the sum means to add them together. So if we sum all of those terms together, we're going to get something like this. If we had an arithmetic sequence like this, A, and then A plus D, and then A plus 2D, we would go up to A plus n minus 1 groups of D. Okay, and again, I think it'll help with an example. This is the same sequence as before. If we need to get to this term, which is 14, it's the 1, 2, 3, 4. It's the 5th term. I need to add, since it's the 5th term, I need to add 4 groups of the common difference. 2 plus 3 once, twice, 3 times, 4 times. So that is our arithmetic sequence up to the maximum value being at A plus n minus 1D. Now, remember the common difference is added n minus 1 times to the first term. I think that can be a little bit confusing because you might think to yourself, you're just going to adding n groups of D, but not quite. You're adding n minus 1 groups of D because you're starting at the first term, not the 0th term. Okay, so it's a little bit tricky and it's a little bit different to general math. So you got to be careful if you're doing general as well. Okay, so what we want to do is we want to sum these together. So basically, we want to add all of these terms together because that is what a arithmetic series is. So we use this notation, capital S sub n would be the arithmetic series, and we're going to add them together. So it's going to be A plus D plus A plus 2D plus all the way up to A plus n minus 1D. Okay, and then you're wondering to yourself, well, what does that equal? Well, let's have a think. What that equals, it needs to be worked out by manipulating some equations here. So what this second line here is this line written backwards. So I've just written it all backwards. of the largest term is first, a plus n minus 1d. All right, then the term before that, I think you would agree would be a plus n minus 2d, all the way back to a. Okay, so that's the series written backwards. And so what we're going to do is we're going to add those equations together. So if we add all the terms together, we actually get this. So that step can be a little bit confusing, but let's think about it. S sub n plus S sub n. Well, that gives us two groups of S sub n, right? So that's just adding the left-hand sides. Okay. The hard part's the right-hand side. So if we look at the right-hand side here, let's see if we can make some sense of it. We're taking this term here, a, and we're adding it to a plus n minus 1d. We're adding the terms, the smallest term to the largest term. So that gives us this. So that gives us two groups of a plus n minus 1d. Okay, and think about how many pairs of those things there are. I think you would agree that there are n pairs of that are going to happen. So what I mean by that is you're going to add this to this, and then you're going to add this to this, and so on, right? And so there's going to be n pairs of that going on. And so what we can say is, or we can say this, we can say we're going to have n groups of 2a plus n minus 1d. And so that gives us, yeah, this is what 2s sub n must equal this, right? And then we just divide the two, we divide both sides by 2, so we get this. So interestingly enough, what we can say is that the arithmetic series adds this, is this, n over 2 multiplied by 2a plus n minus 1d. And then what we just need to realize is that 2a is the same thing as a plus a. But I think you'll recall from before that this part here, a plus n minus 1d, so this part here is the last term. So what we can do is we can call that L. So call the last term L, just to simplify things a little bit. So what we'll get is S sub n equals n on 2 multiplied by a plus the last term. So depending on how many terms you've got, divide that by 2 and then multiply by the value of the first term plus the value of the last term. And that will tell you the, arithmetic series, the sum of all the terms in that sequence up to some value n, right? All right, we're getting there. Geometric sequences. All right, so geometric sequence is a little different. It's a sequence where the next term is found by multiplying the previous term by a fixed amount. So we can, again, generate a recurrence relation. So if we looked at something like this, we said t sub 1 is 2, t sub n is 2 groups of the previous term, 2 times the previous term. So I encourage you to think about what that sequence would be. But I think you would agree you would get something like this. 2 is your first term, and then the next term is generated by multiplying that by 2. So it's going to go 2, 4, 8, 16, 32, and so on, right? Okay, so that's the recurrence relation. Again, what we're going to talk about is the nth rule. How do we work out the nth term is using a formula, essentially? So we'd say the nth term is equal to A, which is the first term, multiplied by R groups. That's not right. A, which is the first term, multiplied by the common ratio, which is R, to the power of n minus 1. And I'll explain that in more detail. Again, A is the first term, R is the common ratio. So if you have your sequence and you look at it, you take some term and then divide by the previous term. 8 divided by 4 gives us the common ratio, which is 2. 16 divided by 8 is also 2. 32 divided by 16 is also 2. So the common ratio is calculated using this. Take some term and then divide by the previous term. Now, just to explain this in a little bit more detail, let's have a look at an example of sort of this rule here. See if we can find the 10th term of this sequence. So again, same sequence. Okay, we're going to use this rule, and then we're just going to see that it works, right? So we take A, which is the first term, which is 2, and then you multiply by the common ratio, which is 2 raised to the power of n minus 1. We want the 10th term, so we do 10 minus 1, which is 9. So we get 2 times 2 to the 9, which is just 2 to the power of 10. So the 10th term is 2 to the power of 10 in this case. And what we can say is we can actually just generate that sequence. 2, 4, 6, 8, 16, 32, 64, 128. You get the idea. You've played this game as a kid. How far can you double it? Anyway, that's the first 20 terms. And I think you would agree, again, that that's the 10th term. It's the 10th term there, 1024. So I just want to explain this a little bit more, why it's n minus 1 and not just n. Remember, if we need to get from 2 up to 1024, I need to actually multiply 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have to multiply by the common ratio n minus 1 times to get to the term that you're interested in. And obviously you're starting at some value a. So it's a multiplied by the common ratio raised to the power of n minus 1. Okay, so that is what a geometric sequence is. Next up, geometric series. So again, just like an arithmetic series, a geometric series is when you sum all the terms, but this time it's in a geometric sequence. So let's see if we can do that. Let's look at an example of a geometric sequence. Again, 2, 4, 8, 16, 32, classic geometric sequence. If we were to write it generally, we would say this. We've got some first term a, second term is going to be a times r squared, a times r cubed, all the way up to a times r to the n minus 1, which is what we just spoke about earlier. So again, remember that the common ratio is multiplied n minus 1 times to the first term. Again, just like before, when we needed the 10th term, we multiplied by the common ratio 9 times. Okay, now what we want to do is we want to work out the sum of all the terms. We want to work out the sum of all these terms in a geometric series. So here's our geometric series layout. Again, it's a series, so we're adding them together now. We're going to add all these together. Okay, and what we're also going to do is we're going to create another equation where we multiply everything by r. So we're allowed to do that, and it's just using a little trick of mathematics to help us work some things out. But if we multiply both sides by r, we can generate another equation, which is this equation here. And just note that when you multiply this last term by r to the n minus 1 multiplied by r is just r to the n. So that's what you get there. Okay, then what you can do, again, as long as you don't break any rules, you can take away equation 1 from equation 2. So we're actually going to get this. And let me explain how this works. I think the left-hand side is quite easy to understand. We take equation 2, r multiplied by s sub n minus s sub n. So that's just this. Okay, equals this. Now, how do we get this term? Well, let's think. If we line these up, right, I think you'll notice that certain terms are going to cancel out. Look at this. AR, or let's start here. RA minus AR, that's going to go to 0. AR squared minus AR squared goes to 0. AR cubed minus the other AR cubed that would be here would go to 0. So in fact, the only thing we're going to be left with is going to be AR to the n and A. So we're going to get AR to the n minus A. Again, this one here would cancel out with the term that's previous to AR to the power of n. So they're the two key terms. We get AR to the n minus A must equal R, must equal, yeah, this left-hand side that we already spoke about. Okay, take out S sub n as a factor, and you get this. So S sub n multiplied by R minus 1 equals AR to the n minus A. Okay, divide everything by R minus 1, and you get this. Okay. Okay, if you, and that's totally fine. That is the geometric series. That is how you work out the geometric series. Again, A is the first term, R is the common ratio, and N is the term you're interested in. But you can also multiply the top and bottom by -1. So if you multiply top and bottom by -1, you'll get this. And this is the same, it's the exact same thing, obviously, but you use this if R is between -1 and 1. It's just a little bit easier to use if you've got R values between -1 and 1. Okay, so this is the key takeaway here. This is how you find, yeah, the sum of a geometric sequence. All right, next one. All right, so an infinite geometric series is the sum of infinitely many terms in a geometric sequence. So sometimes the sequence goes on forever. If you're not interested in stopping at a certain term and you want to continue it forever, you would call that an infinite geometric series, and you want to add those together, and that's actually something we can do. So an infinite geometric series is convergent if the sum of the first n terms approaches a limiting value as n approaches infinity. So this will occur if your R value is between -1 and +1, and I'll show you why that's the case. If you consider this example, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, and so on. I think you would agree if you were to add those together, well, let's think. Firstly, let's just point out the common ratio. Hopefully you realized a half multiplied by a half is a quarter, multiplied by a half is an eighth. So the common ratio is 1/2, which is between -1 and 1. And here it is if we started to add them together. Let's imagine we just had the first term. It would just be 1/2, right? All right, if we took the first term and added the second term, which is 1/4, we get a half plus a quarter, which is 0.75. All right, now we can keep going. We can get a half plus a quarter plus 1/8 actually gives us 0.875. And then we add 1/16 gives us 0.9375, and so on. If we make n really large, you'll notice we get something like this. And you might think to yourself, okay, what is this approaching? And I think you might have a guess. Seems to be approaching the number 1, right? So as n gets large, this approaches the number 1. Seems to be approaching the number 1. And what we want to do is prove that. So if we talk about a proof now, let's take what we learned in the previous part and say, all right, we know that a geometric series has this sum. So we already know this from before. And what we do is we just expand that a in. Okay, let's think. Let's just look at this. As n gets really large, we take a number that's between -1 and 1, and we raise it to a really large number. Well, that's going to get really small, because if we take a half and raise it to the power of a massive number, we're going to get 1 over a really large denominator. So that's essentially going to be 0. So you're going to be left with a over 1 minus r, because this term is essentially 0 if n is large. So as n approaches infinity, the geometric series approaches a on 1 minus r, which I think is an interesting result. And, just to use an example here, let's do this example, obviously. As n approaches infinity, same. The geometric series approaches a on 1 minus r. And so, yeah, let's look at this sequence. This sequence. So we've got the first term a, which is 1/2, over 1 minus 1/2. Okay, 1 minus r, the common ratio is r, right? So we get that the geometric series is approaching a half divided by a half, which is 1. So as we said already, this sequence is in fact, this series, I should say, is in fact approaching the number 1. So I think that's pretty nifty. And that is how you work out an infinite geometric series. Okay, the last part. All right, so this is where it's going to get a little bit tricky. So we'll just do our best. So combined recurrence relations. So basically now we've got some common ratio and we've got something that's going to be added. So again, R is the common ratio, D is this common difference. So let's just look at an example to sort of break things down for now. Here we have the recurrence relation. And R at the moment is 1.8, but we can change that. And D, if we put D to 0. Okay. what you'll notice is if R is 1, let's say R is not 1. If R is 2 and D is 0, then we just have a geometric sequence here, or geometric recursion relation. If R is 1 and D is something else, then I think you would agree we have an arithmetic series, an arithmetic sequence, or an arithmetic recursion relation, right? So this is why it's combined, and we can obviously have any variation of that. Now, if we have this being a 2 and R being a 2 and D being a 2, then it's a combination of a arithmetic and geometric sequence recursion relation. So what we're going to say from there is, well, we're going to say to ourselves now, this is going to be challenging, but that's the recursion relation for a combined recursion relation, but we want to find the formula for the nth term. So if you notice in the previous ones, we've been able to find a formula for the nth term. That's what we want to do for this when it's combined. It's not going to be straightforward, but we'll do our best. So again, here is our recursion relation. If we were to consider the previous term, we know the recursion relation says to get the next term, multiply the previous term by R and add D. So T sub n minus 1 would be equal to R multiplied by T sub n minus 2 plus D, because the previous term to T sub n minus 1 is T sub n minus 2. So that's a key fact we're going to need. And then what we're going to do is we're going to substitute that in to the recurrence relation. So substitute T sub n minus 1 into the recurrence relation. And that gives us this. So we get R multiplied by R, T sub n minus 2 plus D. Expanding that out gives R squared, T sub n minus 2 plus RD plus D. And now what we also want to recall is we're just going to do it again, and we're going to notice a pattern that's going on here. So if we wanted T sub n minus 2, that'd be R T sub n minus 3 plus D. Okay, and then we're going to substitute that into the recurrence relation again. And we're going to notice a pattern. So again, we're taking T sub n minus 2 and subbing it into the recurrence relation. So it gives us R squared, R times T n sub n minus 3 plus D plus RD plus D. Expanding that out, we get this. And then generalizing from here, well, let's think about what's going on. We've got that we take the common ratio to the power of 3 multiplied by T sub n minus 3. So we can see that if we were to consider going from T1 to T2, well, we'd be multiplying by R. I think you would agree with that. Then T1 to T3, we'd be multiplying by R squared. All right, so just generalizing from that a little bit, we would say, therefore, from T1 to Tn, we're multiplying by R to the n minus 1. So yeah, and that should make sense, because to go from 1 to 3, you multiplied by R squared. So to go from 1 to n, you multiply by n minus 1, one less than the nth term. Okay, so similar for the common difference. To go from T1 to T2, you add D. To go from T1 to T3, you would add R groups of D. Yeah, so trying to generalize it is tricky, but what we're saying is every term, so for example, take term 3, that contributes an R squared. So if we're going to the nth term, as we said, that's going to contribute, you're going to multiply by R to the power of n minus 1 times. So that's just for sort of the geometric part of it. You multiply the first term by the common ratio n minus 1 times. And then for the sort of common difference part, well, again, here, if you're going from T1 to Tn, you're going to add the common difference and the number of times equal to r to the n minus 2. So what we end up getting is an infinite geometric series inside here. Inside this bracket here is actually an infinite geometric series. I'm just trying to think how to explain it better. One sec. Yeah, so obviously I've taken d out as a factor here, and then you're left with these terms. So I think you would agree that this is a series. This is an infinite geometric series. And again, the reason r to the n minus 2 is the largest term is because of this. So because of sort of this example, if we're going from T1 to T4, you're adding d r squared times. And so if you're going from T1 to T sub n, you're actually adding d r to the n minus 2 times. And so this is an infinite geometric series. And so then we draw on some of the stuff we learned before, just in terms of simplifying this. This is just from the infinite geometric series section. So you take this, you substitute in the relevant things. Okay, A is the first term. Now, the first term is actually r to the n minus 2, as you can see here. This is the first term. Okay, then you're multiplying by 1 minus r to the n. But the common ratio is r to the negative 1. And again, I just want to explain that. The common ratio is r to the negative 1 because if we take this and divide by this, again, the common ratio, this divided by this, you would get r to the negative 1. And then we're raising that all to the power of n minus 1 because there's actually n minus 1 terms in the geometric series. And then you divide by 1 minus the common ratio, which is r to the negative 1. So from there, oops, you just simplify things a little bit. Expand the brackets up here, get a pen and paper out, see if you can work it out. And then basically our conclusion is it gives us something like this. And so this part in here is an infinite geometric series where the sum is equal to that. Yeah, r to the n minus 1 over r minus 1. Putting it all together, taking this line here and substituting in this because this is what the brackets equal. So you get t sub n equals r to the n minus 1 multiplied by t sub 1 plus t multiplied by r to the n minus 1 over r minus 1. So I think that deserves a box. It's hard to explain, but the maths obviously works out. So good luck. Talk to you soon.